This matter is made up of atoms. Atoms were previously thought to be the smallest particle until the discovery of the protons, neutrons, and electrons. This atomic model leads to one of the biggest questions in physics. How does the nucleus of an atom remain closely packed together despite the repulsive forces of the particles with similar charges like the positively charged protons inside the nucleus? In search for the much stronger force that binds them, physicists discovered quarks and gluons. This is a nucleon, and inside this are quarks. Nucleon is either a proton or neutron. There are 6 types of quarks: up, down, top, bottom, charm, and strange. All of these quarks have corresponding antiquarks. Quarks have mass, electric charge, and color. In terms of electric charge, an up quark has a charge of positive 2/3 while a down quark has a charge of negative 1/3. Since a proton is composed of 2 up quarks and 1 down quark, then the electric charge is positive 1, while the neutron is composed of 2 downward quarks and 1 upward quark, which is equal to 0. Pauli's exclusion principles say that 2 quarks cannot occupy the same place at the same time. How is it possible for the 2 up quarks to be present in a single proton? The answer lies in the third property of quarks, the color. Just kidding! The color property of quarks and gluons is completely unrelated to the colors in the color wheel, but rather, it is just a representation of a different kind of charge, the color charge. The color charge has 3 values, which are red, green, and blue. These values make the quarks inside a single proton distinct with each other. The quarks inside a nucleon carries either red, green, and blue. The quarks are constantly moving, so there must be some force that keeps them contained. And those particles are called gluons. Gluons are the particles of the strong force. Quarks interact by emitting and absorbing gluons. Quarks constantly change color charges as they exchange gluons with other quarks. This interaction creates a very strong color force field which binds the quarks together inside the nucleon. The strong force will become stronger the more the quarks move further apart. Despite the strong force, some quarks can move out of the nucleon. A new quark will replace it to maintain the 3 quarks that make up the nucleon, while the one that got away will be paired with an antiquark. The quark-antiquark pair is called meson. The strong force carried by gluons turns out to be the strongest force in the universe, and it is also the force that holds together protons and neutrons in the nucleus. What? The strongest force in the universe can be found in the smallest particles.